Hello everyone. In this lecture, we would like to discuss generative model. The slide of this lecture is primarily based on two references. One is from MIT course, the other is from Lydian's blog. Up to now, we have talked about two major types of the machine learning, supervised learning and unsupervised learning. In the supervised learning case, the goal is to learn a function which can map the data X into a truth label Y. The question here usually provides the learning goal with a ground truth label. The goal is try to train a model to map the input data into the truth label. The example of the network on this supervised learning is classification problem, for example, to identify a quark from a gluon, and regression problem, for example, to estimate the energy of an electron, or the object detection and semantic segmentation. In the unsupervised learning case, the goal is to learn the hidden or underlying structure of the data without labels. The example of unsupervised learning, including clustering or feature extraction and dimensionality reduction. Today, we want to talk about another type of the model, generative model. The goal is to take input training samples from some distribution and learn a model that represents that distribution. There are two major types of the application of a generative model. For example, density estimation. The input data could be a distribution of the data set. They could follow a particular distribution, P data of X. The generative model can learn a function. This function is a model which can be used to describe the distribution of data. The second application for generative model is sample generation. You could start from an image set, which is input trained samples. The model can learn to generate fake image based on the feature of the input trained samples. Either density estimation or the sample generation. It follows an idea that the network will try to learn a model which can represent a similarity to the distribution of the input data set. There are several types of generative models. In this lecture, we will focus on two types, autoencoders and variational autoencoders. The second type is generative adversarial network. Let's start with autoencoders and variational autoencoders. The autoencoder composed of three components. First, you have an encoder. This encoder can take the input data, compress that into a lower dimensional representation of the input. This lower dimensional input is called bottleneck. Then there's a decoder which can take the bottleneck to uncompress the data in order to produce the output, and this output will be as similar as possible to the input. Therefore, the bottleneck hidden there forces the network to learn a compressed latent representation, and we are able to reconstruct information from this compressed latent representation. The loss function of autoencoder is defined normally based on the mean square error. Compare pixel to pixel difference between the output of the data to the input of the data. With the autoencoder, you are able to use the smaller dimension of the representation, which can capture all the information of the input data, and we can just carry this smaller dimension and to rebuild the large or the original data set comparable to the input data. This is very useful. For example, the telecommunication, when a message try to transfer through a network, either it's the Wi-Fi or the cable network. With such an autoencoder, you can just pass the compressed data set, and you have a protocol to understand how to uncompress the data set in order to reconstruct the original information. Then, use this way, you can speed up the transformation speed. The variational autoencoders is a probabilistic variation on autoencoders. It samples from the mean and standard deviation to compute latent sample. We can visualize these variational autoencoders using this architecture. So instead of learn the compressed low-level dimension, what we learn is a vector of the mean and a vector of a standard deviation of the latent vector. With such a variation, some flexibility to learn the latent vector. So instead of learning the fixed quantity of the latent vector, this encoder will learn a distribution of the latent vector. And this probabilistic encoder, the probabilistic encoder is based on the conditional input of the input data. To uncompress information, we can use a probabilistic decoder and obtain the output image. The loss function of this the loss function of this variational autoencoder are composed of two terms. One is the mean square error of the output data to the input data pixel to pixel. This is the same as the autoencoder. It will add a regularization term, which is based on variational of the latent vector. And the variation of this latent vector is normally chosen as a normal distribution, that is a Gaussian distribution, with the mean value mu and the standard deviation sigma. The advantage of this variational autoencoder is possibility to rebuild the original information even the input data set have some defect. For example, if you have a full image, but a corner of the image is cropped out, with a variational autoencoder, you are still able to rebuild what the missing pieces could be. There's an issue. The issue is that the backpropagation is not allowed. Variation nature is based on a normal Gaussian smearing. In order to compute the backpropagation, we need a deterministic calculation. The way to solve a breakthrough has been introduced to solve this technical problem. That is beta variational autoencoders. Here, there's a trick introduced to parameterize this Gaussian smearing. A fixed mu vector and a fixed standard deviation vector can be scaled by a random constant epsilon drawn from prior distribution. And this prior distribution usually choose as a normal Gaussian. That is, the mean is centered at 0 and the width of this scaling function is unity. With this random constant epsilon, we are able to introduce variation of the sample latent vector. We are also able to have a deterministic nature because the epsilon here is a predefined constant. Therefore, using the beta variational autoencoders, it enables capability to do the backpropagation. Also, it has the property to introduce variational component of the latent vector. Let's take a special look of the loss function of the beta VAE. As commented earlier, the loss function is composed of two terms. One is the reconstruction loss. It's the same as the autoencoder. We just calculate MSE of the output with respect to input. The Second term, which is relevant, is a regularization term. This loss enforces Gaussian latent space. It uses the KL divergence to construct the latent space loss function. The KL divergence is a measure of how one probability distribution is different from the second one. A normal choice of KL divergence is based on the normal Gaussian, which can encourage encoding to distribute encodings evenly around the center of the latent space. Introduction of this beta vector can control the constraint coming from the regularization term. This normal Gaussian can be written as this formula. More detail of the derivation of this formula can be checked. Function is beyond the scope of this lecture. However, in the end of this lecture, we provide references for interested reader to dive in detail. The advantage of this, a major feature of the introduction of beta is the control of the regularization. When beta equal to 0, that's equivalent to the original autoencoders. The variation is not introduced into the loss function. The larger the beta, the larger the regularization term. Each regularization term usually represents a particular type of the each regularization term usually carry the information to control a particular feature for the variational autoencoder. In summary, a variational autoencoder compares representation to something we can use to learn. The reconstruction process allows us for unsupervised learning. This is unsupervised learning because the learning of the output here does not carry the label. In order to implement the VAE, it's required to introduce reparameterization trick so that training become possible. VAE can interpret hidden latent variables using perturbation, that is, introduce this normal Gaussian union on the construction of the latent space learning. Using the VAE, it allows us to generate new examples because of the variation nature on the input latent space. And because of this, it introduced major difference between the autoencoder and variational autoencoder. Let's move to the second generative model, generative adversarial network. Generative adversarial network, also called GAN. GAN is composed of two models. GAN composed of two neural networks competing with each other. One is the generator network. It takes the random noise input and generate fake data. Second is a discriminator. This discriminator will take a train set, which is the sample we target to learn, and the fake data. Discriminator will learn how to identify fake data from the true data. The goal of the generator here is to trick the discriminator, determine the image. The goal of the generator is to produce a fake image, which you can trick the discriminator, failed identification, a fake from the real. Therefore, the training of this GAN network is adversarial objectives for discriminator and generator. Generator will try to reproduce the true data distribution. This means it will try to synthesize. Generator tries to synthesize fake instance that for discriminator. Discriminator tries to identify the synthesized instances. To implement GAN we can look at the loss function definition of the discriminator as the first step. The input of the discriminator is true data set and the generative data set, or we call it fake data. The output of discriminator is to determine the data is real or fake. The loss function of discriminator can be constructed from the discriminator score. The discriminator score, when the input is the true data, this discriminator score value is aiming to be close to 1. That is at the maximum. While the input of the discriminator come from the fake data, this score of a discriminator tend to close to 0. Therefore, it will maximize 1 minus discriminator value up. The loss of the discriminator is to maximize the discriminator with the true input data and 1 minus discriminator value, while the input data is the fake data. To train a generator, it will a random noise as input and generate the fake data. The generator will try to maximize the generator G is trained to increase the chance of the discriminator producing a high probability for a fake example. That means the generator purpose is to bring this discriminator input while input is coming from the generative data close to 1, and it equivalent to minimize 1 minus the discriminator value. In summary, a generative adversarial network is a mini-max gain on the loss function definition. It will try to maximize discriminator. Therefore, it will maximize the loss of this binary cross-entropy definition. In parallel, the generative model will try to maximize the probability of a discriminator output given fake data input. That means minimize 1 minus the discriminator value output. For the discriminator to fail, determine this fake data from the true data. The competitions of the generator and discriminator is the key of the game model. In summary, we introduced 2 generative models. BAE will learn lower dimension latent space and sample to generate input reconstruction. For game, it has 2 competing neural network. Generator network try to generate the fake data to fool the discriminator network. How good the game model is? This is a fun website. Collect all the images. They are all fake images. They are all fake images. They are all fake images generated from the game model. In this week, we will try to exercise a game model application on particle physics. The data is a digest production from LHC Olympic exercise. The sample we are dealing with, the sample are produced from the proton collisions. The sample is produced from the proton collisions into a heavy extended gauge boson W prime. This W prime is unstable decay to 2 particles X and Y, while X can further decay to quark-quark pair and Y can decay to another quark-quark pair. The mass of the X particle is 500 GeV. The mass of Y particle is 100 GeV. When the 2 particles they heteronize into a spray of the particles, we can introduce a jet clustering algorithms with a jet radius 1.0 and require the transverse momentum of the jet should be greater than 1.2 TeV, and should the rapidity to be less than 2.5 for this for the gain study. So our goal is to provide a generative model can represent the kinematics of the two jets coming from this decay chain. We will follow a digest game paper. This the architecture. The generative network will take input noise, reshape, and upsample with 2 layers, and upsample with 2 consecutive networks, and the output will be flattened in using a hypertangent as the output feature. The discriminator will take the generative model, reshape it, and introduce a couple layers of a convolutional neural network. The discriminator output will have a sigmoid continuous single output. What are we targeting for? The input data can be jet kinematics and the substructure variable for the leading transverse momentum jet. The information from the subleading jet are also used as input for the game model construction. The orange histogram are the input data for learning, and the blue histogram are the generative fake data. Overall, the generated data can describe the input data nicely. Of course, this is just a few epochs of operation. We expect the modeling between the fake data and the input data will be quite similar with a sufficient number of epochs. Finally, I would like to recommend extended reading material for generative model. Alright, this is the last slide of the lecture. Enjoy your lab access today.